Okay, welcome back, everyone. I will, so just one thing that someone just asked me, yes, I am going to post these slides, I will share these slides, I will fix some typos and then share these slides. And so you do not need to worry if the last set of equations that we went through went by a little bit quickly. I am not expecting you to follow every single step in every single equation at this stage. This is kind of the important point, that you understand what goes into these direct detection calculations and where we need to make assumptions and where we don't need to make assumptions. So, okay, so this is the expression for the spectrum. So under standard assumptions, what kind of spectrum do we get? So the usual assumption, as I said, is that this f of v distribution is essentially just a Gaussian. So there are two factors that affect the shape of the spectrum with recoil energy in this case. One is the dependence of the velocity integral on the recoil energy, and the other is the form factor dependence. So you might say, hang on, when I wrote this velocity integral here, there was no obvious recoil dependence, but you remember from the first calculation we did that the minimum velocity is a function, that the minimum velocity that can contribute is a function of the recoil energy. So the lower limit on this integral is a function of ER. So this is what that integral looks like if we write out the limits explicitly. The maximum velocity is set by the galactic escape velocity. The minimum velocity is set by the recoil energy that you're looking at. If we take, so this is the standard assumption that's used to set those limits that we looked at, that the dark matter velocity distribution just looks like this object. This is now a Gaussian integral. If we ignore the effects of the escape velocity, which is usually not a terrible approximation, and take the, unless you're dealing with stuff that is right on the edge of detectability at the low mass end, take this limit to infinity, then we can do this integral analytically, and we get a result that looks like this. So what we expect to see is a spectrum that is exponentially falling with the recoil energy. So there is no bump here, there is no feature. The mass of the dark matter determines how fast the exponential fall off is, but it will always be true. So even for relatively heavy dark matter, going to lower recoil energy thresholds can be valuable because you're getting to probe the energy spectrum where it's highest. So this is just a plot from a couple of years ago about what kinds of spectra you expect as a function of the dark matter mass. This black line is for 5 GeV, and this is 10, 20, 30, 40, 50 GeV. So you see for heavy dark matter, the exponential, the scale height is pretty large. You get this broad spectrum. Your low energy sensitivity is not critical. But for light dark matter, that's where 100% of your signal is. It's a very steep exponential cutoff. Yeah, okay. So we can just do a back of the envelope estimate. Given that I want to get to other stuff, I'm just going to go through this quickly. But if you just put in like just very simple numbers, you can look at this on the slide later. For if I had 100 kilos of xenon, which has an atomic mass of 132, then what kind of total rate should I be getting? It's a function of the WIMP cross section. And you find that that rate ends up being about 10 to the 46 times this WIMP nucleon scattering cross section per square centimeters per year. So as you saw on that earlier slide, the limits currently on this quantity are right around 10 to the minus 46. This is why. So these are all the factors that go into that calculation. But I'll also, just mention briefly, in principle, this signal is also time dependent. The sun is moving around the galaxy, which means that it's moving into an effect of wind that comes from our passage through the halo. So if the Earth is, so we always have effectively this dark matter wind blowing into our faces. If the Earth is moving into that wind, that increases the signal. If it's moving with the wind, it decreases the signal. Similarly, the direction of the wind changes as the Earth rotates. So you should, if you could see a signal, you could in principle see the direction that it's coming from, go around in a circle every 24 hours. That requires you to actually see a signal first, though. But these would be good confirmation strategies. Okay, this is, I'm just going to summarize it briefly. So in general, for what you want for these experiments, you want big volumes. You want high A, except that this makes it harder to see light dark matter. If you have a heavier target, then you start to get penalized on recoil energy. You want low backgrounds. The current big flagship experiments are liquid xenon based. So the signal that they're looking for to measure the recoils is the ionization and scintillation in the detector, and they set the best limits over most of the energy range above 10 GeV. Now there are some competing experiments. Super CDMS is a silicon germanium experiment, so they're measuring a different set of, it's similar, it's still ionization plus phonons. They have a lower atomic mass and can get somewhat better limits for light-dark matter, but really to get to light-dark matter you want new search strategies. It's also worth mentioning that there is an anomaly in indirect detection. The Dama Libre experiment in Italy back in the 1990s saw what appeared to be an annual modulation in their signal, which could be due to the passage of the Earth through the dark matter wind. However, if you take that signal seriously, it should have been seen in many other experiments by this point. That said, to date, there has not been a complete replication of the Dama experiment with the same materials, so there are several attempted replications in progress at the moment. This is basically what the current status of direct detection looks like. Now, this is not the plot that you usually see because it's going down to 10 to the minus 5 GeV instead of stopping at 1 GeV. These lines, so this is from a year or so ago, so this xenon 1 ton line, this lower line here is the actual current limit from xenon 1 ton. You can see all of these other limits are, this is a forecast limit, this is not an actual limit. These other limits are pretty good at constraining down to the GeV scale, but below that there's a lot of open territory through this strategy. This dashed yellow line here is what we call the neutrino floor. That's when we're actually going to we expect to start measuring the neutrino background in our experiments, at which point we'll have to think more carefully about how to distinguish a dark matter signal from backgrounds. And it may be that if we don't find anything at that point, we say, okay, maybe let's do a different search strategy for a while. You can see that the neutrino floor on this scale is a couple of orders of magnitude away from where we are now over most of this high mass range. We're actually getting pretty close to hitting it around 10 GeV. At the low end of the scale, have been a lot of proposals in recent years to try to probe this. This is a very brief summary, so you can look for elastic scattering of the type that we've been talking about for very light dark matter, so below the keV scale down to the eV and milli-eV scale. You can instead look at absorption of the dark matter. I mean, this is model dependent, of course, but you can look for absorption of the dark matter energy onto the background. People have looked at looking at electron scattering rather than nuclear scattering, and of using targets that include superfluid helium, semiconductor materials, superconductor materials, where a very tiny excitation can either move you across the band gap or break the superconductivity. Sort of thing. There's a lot of work being done in intersection with the condensed matter community on building exotic materials that can pick up really, really tiny energy transfers. And for that, I refer you to this big review paper from a couple of years ago, which does not have the very most up-to-date stuff, but it's a good place to get started. Okay, so now I want to briefly say some things about collider searches, and then I want to move on to indirect detection so I can talk about my favorite stuff. Collider searches are another area where there's a huge range of possible searches. If you search dark matter searches Atlas or dark matter searches CMS, you will find a large list of searches. But let me just talk about what the basic idea is. So dark matter we know is stable on the timescale of the universe. So it's definitely stable on the timescale of the LHC. You might think, okay, we're going to look at this diagram, but if this was the diagram, then you don't see an output from this diagram. The dark matter particles will just get out of the detector completely, so that's not very helpful. What you want to look for is missing transverse energy and momentum in combination with the standard model particle that is recoiling against that missing energy and momentum. So most direct dark matter searches at the LHC are mono X, where X could be a jet or a photon or a Higgs. There are also dijet searches where you have more than one standard model particle in the final state. The picture for how these might be formed is, for example, if I have quarks produce two dark matter particles, I can radiate it off a standard model particle from the initial standard model part of the interaction, independent of what the dark matter is doing. And so then I can look for a mono jet or W or Z or gamma or Higgs produced in conjunction with a lot of missing energy. So we could also, if the mediator couples directly to the standard model, we could also radiate, or the final state couples directly to the standard model in some way, we could also radiate these particles off other states, but there'll always be the initial state radiation contribution. So why should we look at the LHC? Well, if dark matter's at the heavy end, having lots of energy, having lots of center of mass energy is a good thing. So, but there's also a very active program looking at lower energy, higher luminosity accelerators in the hope of being able to probe particles that might be lighter, but might be more weakly coupled. So yeah, this is essentially, this is closely related to what I was saying before. So as well as these search strategies where you radiate off visible radiation and then look for missing momentum, you could also have situations where you produce particles that subsequently decay, and the decay chain involves dark matter as well as standard model particles. And this is kind of the classic supersymmetry search. The dark matter is the lightest supersymmetric particle. If I produce heavier supersymmetric particles, then they'll decay away, make some dark matter, also make visible particles. And so I can look for those. I can look for the signatures of a whole bunch of visible particles plus a significant amount of missing energy. Now, there's kind of a general tension here, which is, okay, at the LHC, you can't just take the entire, well, it's very hard to take the entire data set and say, I'm going to do a generic search for dark matter in this data set. You need to specify what kind of signature you're looking for. And there are broadly three general approaches here. In varying levels of model dependence. So one is to say, okay, I have some specific model or set of models. For example, I have the minimal supersymmetric standard model, or I have my other favorite SUSY model. I have a well-defined set of parameters. I'm going to vary over those parameters. I'm going to ask what would my rate for monojet production or dijet plus missing energy production be in this model. And then I'm going to do a search for these signatures. I'm going to recast it into a specific constraint on this model. So the upside, in full complete models, there are often many particles that are not the dark matter that could be within reach of the LHC. So SUSY is sort of the archetypal example of this. There can be very characteristic SUSY signatures that involve cascades producing many particles with large missing energy. The downside, and if you do it in this approach, then you know that you've got a well-defined theory. You don't have to worry in general about violating unitarity or other such strange behaviors. The downside is that if I say to you, right, I have constrained this particular region in the SUSY parameter space, I have constrained this set of parameters among SUSY models, and then I say, right, I have a different dark matter model, how do these constraints apply? Then it can be very non-trivial to generalize these constraints. So the signatures are idiosyncratic. So that makes it hard to do a general search. So in response to this, there's been a lot of work done in recent years to construct what people call simplified models with only a few ingredients. So for example, you might say, suppose I have dark matter, and I suppose I have a mediator, and I can scan over the space of the dark matter mass and the mediator mass, and the coupling between the two. And just try to, just write down the tree level diagrams that I can draw with only those particles and use that to figure out what signatures I can look for. And that can be easy to generalize because you can say, okay, let's test the possibilities. The mediator could be a scalar or a vector or a pseudoscalar or an axial vector. So the upside is that by doing this, you can scan out you can map out what signals you might expect, and you'd reduce the risk of missing a signal because you were searching too narrowly. The downside is that sometimes the extra ingredients that you are missing between this simplified model and a complete model are actually important. For example, a kind of classic issue with simplified models, which I think people have mostly recognized by this point, is that suppose I say, okay, I've got my dark matter particle, and I've got a massive non-abelian vector mediator. Like that's the setup. And I do my calculation, then quite often you will find that unitarity appears to be violated in processes that you're working with. And the reason for this is that you didn't explain where the vector boson was getting its mass. So then you have to introduce some Higgs mechanism, either in the dark sector or some coupling to the standard model Higgs. Introducing that Higgs mechanism means there's another particle in the theory, and there are other diagrams that you need to take into account. And so if you drop that ingredient, you get results that actually don't make sense and that can't be embedded in any UV complete model. So this is just something to be cautious of when using simplified models. There's not actually a guarantee that a given simplified model that you write down can be embedded into some reasonable, more complete theory. The more extreme version of this is to say, well, can we just use an effective field theory approach? Can we just integrate out every degree of freedom except the particles I'm interested in? This in principle is fine, but sometimes you get into a situation where the only masses that you can constrain for the particles that you're integrating out are light enough that you should not have integrated them out. So if they're heavy enough that you can integrate them out, then you find that the LHC can't constrain the process. So it's important to check for self-consistency if you do EFT approaches. So just as an example of what these two scenarios look like, this is a simplified model search from Atlas based on 13 TeV of Atlas data. So they're looking for processes where the dark matter couples to some heavy mediator, which also couples to quarks. They consider different possibilities for the spin of the mediator, which could be vector, axial, vector, scalar, or pseudoscalar. This is for an axial vector mediator coupling to Dirac dark matter. And these different colored regions show the reach of various searches in the plane of the mediator mass in TeV versus the dark matter mass in TeV. So these are mostly dijet searches, these lines over here, and this is missing energy plus a jet, or missing energy plus a photon, or missing energy plus a Z. So this is, and they have a whole set of these results for axial vector for various structures of the mediator and the dark matter, which can be quite powerful. Okay, so then the last thing I want to say on this topic before I go and talk about indirect detection is that it doesn't need to be the LHC. The LHC is great for looking for heavy objects, but the dark matter could be light. As we've said, the direct detection has that huge window open below the GeV scale. So there's been a lot of interest in recent years in looking for either sub-GeV dark matter or dark matter that is with the standard model through light weakly coupled particles and searching for those mediator particles directly. So in that case, you may care more about getting more luminosity than about having very high energy collisions. And you may want to go to lower energy just to reduce your background. So there's a pretty active program of fixed target and collider experiments to look for situations like this, either trying to produce the dark matter directly or just looking for whatever mediates the interaction of the dark matter with the standard model. I'm mostly just going to point you at this report again. But these are some current constraints. So this is for thermal dark matter that gets its abundance through freezing out through some tree level process. So this is essentially just doing this rotation. Really, these black lines are the thermal. So this y-axis is a coupling parameter. The x-axis is the mass of the dark matter in MeV. So this is sort of the 1 MeV to GeV level. These black lines are showing what kind of, in this simplified recasting, what kind of values you need to get the right relic density for scalar dark matter, for Majorana fermion dark matter, and for, it's called pseudo-Dirac dark matter. And up here are the current constraints, and all the dashed lines are anticipated future experiments. So accelerators are a potential way to get into this light dark matter region as well, where direct detection has a lot of trouble. And then this lower plot is a search for dark photons, which are particles like the photon, except they have mass that could mix with the photon through some small mixing epsilon. So this is showing how constrained those particles are as a function of their mass and of the coupling. And these are, again, these shaded so yeah, there's a little bit of a mixture here between actual constraints and forecast constraints. But you can see that, so this is actually something that I was interested in, because one of the first papers I wrote as a PhD student was about scenarios like this. And at the time that we wrote that paper back in 2008, basically this whole window was open. And in the last 10 years, these experiments have pushed down the limit to the level that mixings of between 10 to the minus 3 and 10 to the minus 4 in this epsilon parameter are now getting constrained. But you can see, like, there's still some region open for sort of 10 MeV to 1 GeV particles that mix with the standard model photon at the level of 10 to the minus 4 or 10 to the minus 5. So these are also a class of related searches. Okay, that's what I wanted to say about searches you can do on Earth. Now, in the remainder of my time, I'm going to talk about telescopes. But are there any questions before I do that? Oh, is that a question? Or okay, let me talk about telescopes. No, wait, wrong one. Okay, sorry, which is the... Control F. just Control F. Yeah. Okay, sorry. Control. Okay, good. Okay, so in the last part of this talk, I want to talk, and if you were at my public lecture, you've already heard a fair bit about this. I want to talk about the same process that we talked about earlier in the context of getting the right abundance of thermal dark matter, which is that dark matter could annihilate, producing visible particles, which we could then look for. Now, as well as annihilation, there's also, of course, the possibility that the dark matter could just decay, that it could be unstable. The searches for that are very similar to the searches for annihilation. The meaningful difference is that annihilation scales like 2 powers of the dark matter density, and decay only scales like 1 power of the dark matter density. But so in all of these searches, and this is our only real handle on the lifetime of the dark matter, on testing whether it's absolutely stable or whether it decays with a long lifetime, because in any Earth-based experiment, you will never be able to wait long enough for the dark matter to decay. But if we use telescopes to look at what dark matter is doing out in space, some small fraction of the dark matter can decay, and that's enough. Okay, so I first want to say a little, I want to go quickly again, and these are I'll post the slides, these are notes that you can use for reference later, but I first want to say just a little bit about how you actually calculate signals. If you want to test if your model is observable in these searches, then what do you do? So the way that if we think about uncharged particles first, photons and neutrinos, because they're uncharged, they travel to us in straight lines. This is very nice. It means that if you see a signal, you can identify where it came from. So you can point back to the source. So we can usually obtain 2-dimensional and sometimes 3-dimensional information on the source distribution, and that's a powerful way to try to separate signal from background. For charged particles, you don't have this advantage. As a consequence, the backgrounds are much harder to handle. We generally parameterize the strength when we want to understand, what sources we should look at. We parameterize the strength of a signal from a given source by just how much dark matter there is in it, or what its average value of the dark matter density or density squared is, which we call the J factor. So the geometric calculation here is very simple. So you suppose that I've got some volume element. So suppose that this is me. I think I was told not to use green. This is me at Earth looking out at the sky. I have some region over here that I think might have dark matter in it, and those dark matter particles might be colliding or decaying to make photons. So if I consider a volume element, dV, in this region, I can ask how much of the signal from this volume element would I see? And then I just need to integrate across all possible such volume elements along some line of sight. So the amount of power within this region is the annihilation rate. So the annihilation rate is given up there. If I assume the dark matter is identical to itself, which is the standard assumption in this case, the annihilation rate is just given by half n squared sigma v, which I can rewrite in terms of the dark matter mass density and the mass of the dark matter. So let's suppose that in every annihilation, I produce a number of photons or neutrinos given by dNdE. So this is the particle physics calculation. This is what you work out with Pythia, or your favored program for figuring out, first you do a calculation to figure out what standard model particles are produced, and then you look at how they decay. Then the spectrum produced per volume per time can be written in this form. So we have kind of the particle physics piece and the astrophysics piece, which is just the mass density of the dark matter. So my volume element is radiating this much, but the fraction of this that I see is just going to be the size of my detector, which is area A, divided by the area of the sphere at this radius from the source. So I need to multiply the total power being emitted by this volume element by a factor of A over 4 pi r squared. And that determines how many photons I'll see per that volume element per unit time. Okay, so then when I integrate, so this is geometric factor. Okay, so then when I do the integral over all such volume elements dV, it's convenient to work in spherical polar coordinates that are centered at my location. So this r is now just the radial coordinate. So my volume element has an r squared dr in it. That cancels out the 1 over r squared from this geometric factor. And I just need to integrate the density squared of dark matter along the line of sight, dr, and along whatever solid angle I'm looking at. So then I can write my observed signal in terms of this geometric piece. This is what we usually call the J factor of the system that we're looking at. And this piece that just depends on the mass of the dark matter, the cross-section, and the spectrum per annihilation, which is your particle physics model. For decaying dark matter, it's exactly the same thing. The only thing that changes is that there's a rho here instead of a rho squared. I should note that sometimes in the literature, this J factor is defined with a 1/4 pi folded into it, and sometimes with a 1/8 pi. So like just check what convention the paper you're reading is using, because I know of at least one case where people thought that a constraint on dark matter in clusters was a factor of 10 different than what it actually was, because they messed up the 4 pi convention in the J factor. So it's just, unfortunately doesn't seem to be a systematic convention for this. Okay, so you can look up tables for, if I look at dwarf galaxies or if I look at the galactic center, what are their J factors, and you can use that to infer what kind of cross-section do I need to get a decent signal. I should mention this separation between the particle physics and the astrophysics does tacitly assume that this cross-section does not depend on where you are. If you have a cross-section that depends on the density of some other particle, or if you have some like strong velocity dependence in that cross-section, then this cross-section has to go inside this integral. It has to go inside the space dependence, and so that breaks this factorization a little bit. Okay, so if we want to do estimates with J factors, so the typical estimates for J factors for dwarf satellite galaxies of the Milky Way in the convention that I used on the previous slide is between about 10 to the 17 and 10 to the 20 GeV squared per centimeters to the 5th. The galactic center region within 1 degree, well, I'll give you this number and then I'll explain why it's very poorly known, but if you, the number here is about 10 to the 22 GeV squared per centimeter to the 5. So if we're comparing these numbers, you can see why we look at the galactic center region, we just expect it to be much brighter in terms of integrated dark matter density squared than any other objects in the galaxy. Dwarf satellite galaxies are nice because they're clumps of dark matter circling the Milky Way with pretty minimal baryonic content, so their backgrounds should be smaller, but as you see from this, their signal can also be quite a lot smaller. However, this galactic center estimate assumes that the dark matter density profile behaves like this. This NFW profile, which is 1/r at small radii and 1/r cubed at large radii. This profile is based on fits to simulations that included only dark matter at sufficiently small distance from the galactic center. The potential is completely dominated by baryons, and there's not really a strong reason to think that this profile is correct. At the same time, we don't know what replaces it. So there's a significant uncertainty just in what the dark matter density is doing closer to the galactic center. And so whenever you see a constraint coming from the galactic center, you should look at what they assumed for the dark matter density profile, because it can make a big difference. For this reason, I like to think of galactic center searches as they're basically, the optimist's bet, because if you see a signal, then that's very interesting. If you see a signal, you can potentially infer what the dark matter density profile is if you have reason to think that it's a dark matter signal. But if you see nothing, it's often hard to say much, because it could just be that the dark matter density is much lower than you anticipated. So if we just take an example with these numbers, we say suppose you have 100 GeV dark matter with the thermal relic cross-section that we worked out yesterday, and we say that each annihilation produces around 1 photon in the energy bin that we're looking at. That's pretty conservative. If I produce a lot of hadrons and then they shower, then I can easily get 10 or 20 photons in the energy bin I'm looking at. But let's start with that. Then if I put in this J factor for the galactic center region of 10 to the 22 GeV squared per centimeter to the 5, put in all the other numbers, then I find that my rate is about 10 to the minus 9 photons per square centimeter per second. So a year is a few times 10 to the 7 seconds. So this tells me that if I have a 100 square centimeter detector and I wait for a year, I should see about 1 photon from the galactic center. So to get a meaningful signal, you either need to wait much longer or you need much bigger detectors. This is just a caveat, I'll just say it briefly. If the photons are coming to you from cosmological distances, you need to take into account that they've redshifted along the way. So the photons that you're looking at a given energy may come from a range of redshifts and will have then had a range of initial energies. So in that case, the signal that you see today is an integral, is an integral over redshift. And it takes this form. If you ever need to use it, there's a formula. Happy to talk more about it to people who are interested. So for these photon and neutrino searches, your question then becomes, where should we look, with the zero-thought answer being, of course, you look everywhere. But these are the advantages and disadvantages of each location. So the dwarf galaxies are orbiting the Milky Way. They're relatively close to us. They're also relatively low background. They're generally where the most robust constraints come from for these annihilation searches. The only problem is because they're so small and don't have a lot of stars, it's often hard to estimate exactly how much dark matter they have in them. So those J factors I told you about often have order of magnitude uncertainties. So the signal prediction is somewhat uncertain. The galactic center is expected to have a high signal, albeit with the modular uncertainties on the dark matter density, but the background is pretty high and it's sensitive to this density profile. We can look at the galactic halo more broadly, the cloud of dark matter that surrounds our own galaxy. It's very nearby, we live inside it. It's a large area, so you can get a big J factor from there. The backgrounds are very complicated. There are gamma ray backgrounds in this, so there are backgrounds across the whole photon spectrum that just come from interactions between the charged particles of the galaxy, the stars of the galaxy, the radiation fields of the galaxy, and the interstellar gas. But you can look there and it can potentially give you strong constraints. You can look outside our galaxy, you can look to other galaxies in clusters. These obviously can have very large dark matter content, it's just they're further away, so you pay some penalty for that. They can potentially hold redshift information. You can validate a signal by saying, okay, if we look into clusters, is the cluster that's at twice as high a redshift, are the photons we're seeing from that cluster twice as low in energy? Is it consistent with having the same origin spectrum? These signals tend to be very sensitive to how many, especially for annihilation signals, to how many small clumps of dark matter you have within a larger halo. That's very difficult to probe directly, but those small clumps, which have high local densities, can be the sites of most of the annihilation in the halo. So that's another substantial uncertainty. You can look for, you can do a blind search for just dark matter clumps that have no stars associated with them. On the other hand, there are potentially a lot of these, and they could be a probe of how many of these small clumps you have, which could give us important information about the properties of dark matter, about how fast it's moving in the early universe. The problem here is that if there's no baryonic matter, it's a blind search. You're just looking for hotspots in photons or neutrinos across the sky. And it may be hard to convince yourself that there's really not anything astrophysical there that might be explaining it. And you can look at the extragalactic background radiation. So this holds redshift information. It probes halos at all scales. For setting constraints, it has this issue that it's sensitive to how many very small dark matter clumps you have. But yeah, so that's also a strategy to look. So searches have been done in all of these channels. And when I show you constraints, I'll just show you the sort of selection of what are currently the strongest limits. So charged annihilation and decay products, the situation is more complicated. You can't do this integral over line of sight because our galaxy has significant magnetic fields, and so the trajectories of charged particles when they hit our detectors at Earth come from all directions, essentially isotropically, and it's very hard to trace them back to the sources that they came from. This also makes the signal to background separation a lot harder unless the expected background is really small. So this is true for searches for antideuterons and for heavier antinuclei. For that, you also expect the flux to be pretty small, but there are experiments like the GAPS experiment is going to try to do an antideuteron measurement. So the observable that you do have in general for this is just the energy spectrum of particles. How many are there at a given energy? Your backgrounds are also coming from charged particles propagating through the magnetic fields of the galaxy, so that modeling is significantly more complicated than what it is for the uncharged particles. And these propagation uncertainties affect both the signals and the backgrounds. And these searches can be very powerful, but essentially the question is always, have you correctly captured the systematic uncertainties coming from the propagation of charged particles through the galaxy? So essentially, the strategy generally used here is to treat our galaxy as just a sea of cosmic rays diffusing through the galactic magnetic field. Schematically, what you're doing is just solving a diffusion equation. This has a term for spatial diffusion of the particles through the magnetic fields of the galaxy, which is energy dependent, controlled by this diffusion coefficient D of E. We usually assume it just has a power law dependence on energy. There are losses, the particles can lose their energy. This is a loss term. As B of E is telling you about the scattering rate for particles to scatter on ambient photons or to lose energy due to propagating through magnetic fields. And there's a source term, which could be from astrophysical sources or could be from dark matter. We're generally interested in looking for the steady state distribution of cosmic rays. In practice, we use numerical solvers like Galprop and Dragon to solve increasingly complicated variations of this diffusion equation. So yeah, the simplest version of this approach is just to mold the galaxy as a cylindrical slab, say that at the boundaries of this slab, the cosmic rays can escape freely. You assume isotropic and homogeneous diffusion. The latest version of Galprop is starting to move away from these assumptions, but this has been the general assumption in the field for a long time. At the baseline, you assume isotropic and homogeneous diffusion, and you assume that the diffusion coefficient is just a power law function of energy. Again, we can say a little bit about how parametrically this differential equation works. You're usually in a regime where either the diffusion dominates the evolution of the energy spectrum, or the losses dominate the diffusion, the changes in the energy spectrum. A way to sort of get a handle on how these behave is to say, okay, suppose that my steady state solution, so I'm going to take my steady state solution, so I'm going to say that the actual change of the flux in time should be 0. That gives me a relationship between the source flux and the loss terms. If we assume that this steady state flux has a power law like energy dependence, then the derivative with respect to E just becomes like a factor of 1 over E. If we assume, again, a fairly smooth distribution spatially, we can estimate the second derivative, the spatial derivative, as just 1 over some spatial scale squared. That's going to be set by the boundary conditions if that's your only length scale in the problem. So that gives you a simplified version of the diffusion equation, which looks like this, where the source is just set equal to the steady state spectrum times a loss term from diffusion, which is energy dependent, and a loss term from energy losses. So which one of these processes is faster then basically just determines the steady state spectrum is going to be the injected spectrum of cosmic rays multiplied by a factor which is just set by the time scale for diffusion or the time scale for loss, whichever of these is faster. So what this means is that as these cosmic rays propagate throughout the galaxy, the zeroth order thing that happens is just that their spectrum is tilted by either the diffusion coefficient, by either the energy dependence of the diffusion coefficient or by the energy dependence of the losses. So the expectation is that the diffusion coefficient scales roughly like e to the 0.3 to 0.7, and the loss rate for the loss mechanisms that we know about, which are synchrotron radiation and scattering on the photons, this loss coefficient scales like e squared. So that tells you in the diffusion-dominated regime, your expectation is that the final steady-state spectrum looks basically like the source spectrum multiplied by e to the minus delta, and in the loss spectrum, it looks like the source spectrum times 1 over e. So you can have a situation where the diffusion dominates at some energies and losses dominate at some other energies, in which you sculpt a change of slope in the spectrum. And that can look like a bump if you do it right. So these propagation effects, the zeroth order thing that they do is that they soften the injected source spectra. They make less power at high energies, more power at low energies. But this can occur to different degrees depending on what dominates between diffusion and losses. And so that can also sculpt features in the spectrum. So that's the zeroth order picture of how cosmic ray propagation works. I hope that gives you, but I'm making a huge number of approximations here, but this is what we would need to really understand to be able to properly predict the cosmic ray observations that we see. In addition to also understanding like what the solar system does. The sun also has a magnetic field, and that can also deflect these cosmic rays, especially at lower energies. Okay, okay. There's another class of models where you say, okay, what if instead of looking at these particles directly, we look at how they've changed the universe through its history? If there's dark matter annihilation or decay going on today, then at some level it's been going on for the universe's whole history, most likely. So, for example, these early injections can change the temperature history of the universe. They can change the ionization history of the universe. They can potentially modify Big Bang nucleosynthesis. The advantage of these early universe limits is that they don't depend on modeling galactic astrophysics. You don't have to worry about how particles propagate through complicated magnetic fields. They come from epochs when the universe was essentially homogeneous. However, they're more indirect signals. You're seeing not the direct effects of the annihilation or decay, but something several steps downstream. So that has modeling challenges. I'm just going to skip over this because I want to show you some current limits. So I'll just tell you that those constraints exist, and I'm happy to talk more about how they work. But the baseline is just you change the temperature history, you change the ionization history, you change the abundances of flight elements. Those are the observables that you can look at. Okay, so where do we stand at the moment in terms of current limits? So there's a set of early universe constraints that comes from looking at if dark matter were to annihilate or to decay, it would produce particles that, as they cool down and lose their energy, could photoionize particles after the epoch of recombination. So when the universe was more than a few 100,000 years old. And you can look for the changes that those extra free electrons and extra ions after the CMB is emitted would have on the CMB. We've measured the CMB well enough now that you can get very tight constraints from this. And in particular, the thermal relic cross-section is essentially ruled out for dark matter lighter than about 10 GeV, unless you have a significant branching ratio into neutrinos. So this is from the Planck collaboration last year. This plot is the cross-section on the y-axis, mass of the dark matter on the x-axis. The black line is the estimated cross-section that gives you the right relic density. Now, of course, this is not a compulsory number. As we talked about earlier, the annihilation rate at late times could be higher or lower than this value, even if it is a thermal relic. And of course, it doesn't necessarily have to be a thermal relic in the first place. But if it is, then these colored lines show that above each of these colored lines corresponds to a different standard model final state, and the region above these lines is excluded. The red and pink lines are for annihilation directly to electrons and photons. This band of densely spaced lines is every other final state in the standard model except neutrinos. So you see that these lines cross, the highest of these lines crosses the thermal relic line at about 10 GeV, and this just keeps going down to about the keV scale, where the cross-section limit is essentially proportional to the mass. So this essentially tells you that if the dark matter is lighter than about 10 GeV and annihilates back to standard model particles, its cross-section during the epoch when the CMB is being released should be well below the thermal relic value. That can be because it's non-thermal, or because it was asymmetric, it had anti-dark matter in the early universe and now the anti-dark matter is all gone. It could be because the cross-section is velocity suppressed at late times. So there are various ways to do this, but it places a significant constraint on dark matter models in this MEV to 10 GeV thermal part of the thermal range. Okay, so below 10 GeV, the CMB constraints are usually the first thing that you should be worried about. Above 10 GeV, we have sensitive observations of photons from the Fermi Gamma Ray Space Telescope and of cosmic rays from the AMSO2 experiment. So in particular, if my standard model particles that I produce in my annihilations are dominantly hadrons or objects that can decay into hadrons, when these particles decay, they tend to make a lot of pions. The pions decay and make a lot of photons, and so these channels tend to make a lot of gamma rays that you can observe with the Fermi Large Area Telescope. So this is an example. So this is an example constraint from looking at the galactic halo with the Fermi Large Area Telescope. The black line is the solid black line is this group's study of the halo. The dashed black line is a study of the dwarf galaxies in Fermi. You can see that this is for one particular channel. This is for annihilation into B quarks, but annihilation into other quark channels will give fairly similar constraints. And then this horizontal line is the thermal relic cross-section again, and you can see that it crosses the line around about 100 GeV. So thermal relic cross-section, using it as a benchmark, is excluded below 10 GeV by the CMB, and then in the 10 GeV to 100 GeV region, Fermi observations of our galaxy and the dwarf galaxies can test cross-sections at that level. Now, what Fermi and other gamma ray telescopes are bad at looking for is final states that are rich in leptons, like in particular in muons and electrons, because muons just decay to electrons and neutrinos. They don't make a lot of photons. Electrons and positrons don't decay at all. So those channels tend to be most constrained by the AMSO2 experiment, which is on the space station, and it measures the flux of charged particles in our neighborhood. But because there are large uncertainties on those limits from the propagation uncertainties, they can only, for annihilation to muons, you can only rule out the thermal relic cross-section below about 20 GeV. And above that, the space is pretty open. if you look at, so for hadronic channels, as well as producing photons, they also produce charged particles, antiprotons, and protons. So AMS also measures the antiproton spectrum, and that, if you think you understand the systematic uncertainties in the cosmic ray propagation, you can potentially extend the constraint on that channels up to several hundred GeV for a thermorelic cross-section. Again, the thermorelic cross-section doesn't have to be the answer, but it's a convenient benchmark. This also constrains higher or lower cross-sections, just at a different mass range. So this is an example of the constraint that you get for dwarf spheroidals from the Fermi observation of dwarf galaxies for annihilation to B quarks. So that's that red line. This is what we looked at earlier. You know, this scale is now 1 TeV. This is 10 TeV. The blue line is the constraint that you would get from looking at AMS antiprotons, modulo some estimate of the systematic uncertainties in the propagation. There's also, in this antiproton measurement, a hint of maybe an excess. At low energies, so in about 20 GeV antiprotons, there appear to be somewhat more antiprotons than you thought there should be. And there's maybe kind of a bump-like structure, but it's not very high significance. If it was dark matter, what you would want is a cross-section that's around the thermorelic value. So this contour plot is showing the favored region in cross-section and mass space would correspond to a dark matter mass between about 40 and 130 GeV. That said, there have been a bunch of papers on this recently. Some of the papers say the significance is 5 sigma, others say the significance is 0 sigma. The difference between these two analyses is essentially what you assume for the systematic uncertainties in the propagation parameters and what you assume for the correlations between different energy bins in the data set, which the experimental collaboration has not released, so everybody's guessing, basically. So as maybe something to keep an eye on. I'm happy to chat about that more, but yeah, it's the range of significance levels is quite impressive. It really does reach from 0 to 1 sigma all the way up to 5 sigma, depending on what you think your systematic uncertainties are. For decaying dark matter, you can do similar searches, again at the GeV and higher scale, looking for gamma rays and looking for cosmic rays, set pretty stringent limits. So for annihilation, as you go to higher masses, you reduce the dark matter number density, and that reduces the signal. For decay, your number density is inversely proportional to mass, but your power per annihilation is proportional to mass, and these roughly cancel out. So for decay, all the decay lifetimes below this red line are ruled out by gamma ray observations of a range of different sources. This plot goes from about 10 GeV up to 10 to the 10 GeV, and across this whole range, we can constrain lifetimes that are shorter than about 10 orders of magnitude longer than the age of the universe. So around 10 to the 27 to 10 to the 28 seconds. This is for decay channel. Again, it's hard to see decay purely into leptons in these channels, so this is for hadronic decay channels. For sub-GeV dark matter, you can keep extending this lifetime down so long as you make plenty of photons. If you decay mostly leptonically, there's a weaker lifetime limit, but it's pretty robust and stretches over the whole range from cosmic microwave background bounds at a lifetime of about 10 to the 24 to 10 to the 25 seconds. So if the dark matter decays into standard model stuff, its lifetime is probably at least 8 orders of magnitude longer than the age of the universe. Or we would have seen the signals. Okay, so I imagine people want to have lunch, so I'll just say a few things briefly. So that's basically where we stand on constraints from indirect detection. We have a range of constraints across a range of channels. If you want to, for decay, if you've got any decaying dark matter that has a lifetime shorter than about 10 to the 27, 10 to the 28 seconds, you should check against indirect detection constraints unless it decays invisibly. For annihilation, if you have a thermal-ish cross-section at mass scales below 100 GeV, you should either suppress that cross-section at late times, or you should think about how it interacts with these indirect detection limits. So indirect detection is also kind of famous for having anomalies pop up, which may be astrophysics or may be dark matter. So there are a few of these around at the moment. I've mentioned one already, which is the antiproton case. This is another one that's been around for a few years. There's a claim that there is a 3.5 keV X-ray line, which was observed initially in a stacked sample of galaxy clusters back in 2014. So they have some nice evidence that this constraint is not just an instrumental effect, because it's been seen in multiple different instruments, and it's also, the clusters are at different redshifts, and you can check that you only see the signal when you properly correct for the redshift. you probably correct for the energy shift of the photons. There are, if you ask what this could be if it's not dark matter, there are some atomic lions. There are some atomic lions in this broad energy range. There are arguments that these atomic lions are probably somewhat subdominant, but there are uncertainties there. The simplest dark matter explanation is that we're looking at some kind of sterile neutrino at a mass of around 7 keV, and in which case it would be decaying to a 3.5 keV photon and a 3.5 keV neutrino. This is a review from a couple of years ago by Kevork-Abazagian showing the mixing angle of the sterile neutrino with the standard model. So this is like a coupling on the y-axis, and the mass on the x-axis. This is 7 keV here. This band only goes from 6.6 to 7.5 keV, so it's pretty narrow. And these are colored regions of various claimed detections, and the solid lines are constraints. So broadly speaking, there's a broadly consistent picture where this could be a dark matter decay signal, but there are also significantly debated constraints that, if taken seriously, rule out most of the available parameter space for this to be a decay signal. There were 2 papers just in the last 6 months, one of which said we can put a constraint line on this plot down at this level, and then another paper which said, oh, but you know, they didn't do their background modeling correctly. If you do the background modeling correctly, the limit goes up to here and is consistent with this signal. The good news about this signal is that there's a way to test it from data. We know exactly what we need to do. What we need is an X-ray observation of this line that has a better energy resolution, because it's meant to be a sharp spectral feature. It's meant to be a sharp spectral feature. So if you can get a good enough energy resolution, you can ask, is this actually sitting right on top of any of the neighboring lions? Some of the potential backgrounds are actually structures of several lions. You could potentially resolve that with better energy resolution. And if your energy resolution is good enough, you can look for the broadening of a dark matter line that comes from the velocity dispersion of the dark matter in the galactic halo, just the Doppler broadening. So there are a couple of possible instruments scheduled for around 2021, which could get a handle on this. The one that I know more about is the Micro-X sounding rocket, which has a dark matter search flight that's scheduled for 2021. So this is basically, you put a very sensitive X-ray spectrometer on a rocket, it goes up, it flies for about 5 minutes, and then it comes back down. You retrieve your X-ray spectrometer, and then you do it again, hopefully. The advantage of this is that it's much cheaper than putting stuff in space. And it turns out that despite the short exposure, you can actually get you have a pretty large field of view, you can look at the whole galactic halo, you can potentially get very good energy resolution at the 10 to the minus 3 level, so 3 eV on top of a 3.5 keV signal, which would be enough to start seeing this Doppler broadening. So I think that their plan is that with one 5-minute flight, they could hope to see a 2 sigma excess. And if they saw a 2 sigma excess, they would say, please, NSF, give us more money, let us do this again. Or they could get a fluctuation the other way and exclude this. There was a great Japanese mission called Astro H or Hitomi a couple of years ago that was going to resolve this signal completely a few years back, but unfortunately it broke apart shortly. It was a satellite experiment, and unfortunately it broke apart not that long after launch. So we still don't have an answer. But the successor mission to that, I have been told Japan is trying to do a successor mission also in 2021. So stay tuned, but hopefully in a couple of years we might get final certainty on this signal. There's also, I'd mentioned the AMSO2 antiprotons earlier. AMSO2 also sees a pretty large flux of high energy positrons. This is not really expected from secondary production. We expect positrons to come from protons hitting the gas and making positrons. So we would expect those positrons to typically be lower energy. So this has been extensively discussed as so this seems to indicate that there's some primary source of positrons that don't come from protons hitting the gas. Now, this has been extensively discussed as a possible signature of dark matter going back to 2008 when this signal was first detected by the Pamela experiment. But I think there's now reasonably good evidence that this probably comes not from dark matter, but from nearby pulsars, which can produce up to TeV scale positrons. The evidence for the recent change in this is that The Hawke telescope, which is a high-energy gamma ray telescope, found extended gamma ray emission around 2 nearby pulsars. The hypothesis is that that gamma ray emission comes from positrons and electrons streaming off the pulsar, which then upscatter the photons around the pulsar up to gamma ray energies. So from looking at these halos, you can infer what the spectrum of high-energy electrons and positrons needs to be. And it tells you that these pulsars, which are not very far away from us, like a few hundred light years, are producing large amounts of TeV scale positrons. So these papers argue that from these measurements, there's a pretty good, if we see a big flux of positrons and we know that there are sources a few hundred light years away producing lots of TeV positrons, then there's probably a connection. And they show some models where they show some models and propagation models where they can explain essentially the whole AMS excess from these pulsars. It's still not a total slam dunk. You need to assume some somewhat strange propagation properties. The fact that we see these halos at all is actually very unexpected, because under the standard propagation assumptions, you would expect that these pulsars just stream away from, that these positrons just stream away from their source pulsars and get a long way before they stop. So they shouldn't be making a tight halo around the pulsar. So I think the current story is that you expect that these pulsars are surrounded by regions of impeded diffusion, so the positrons get stuck there for a while, but then eventually they leak out. But because we don't really understand in detail how this works, there are some knobs to turn there. And by turning those knobs, you can enhance or suppress the fraction of the AMS excess that comes from these pulsars. But I mean, at this point, I would be willing to bet that it's probably coming from these sources, just Occam's razor. Okay. Now, it's 10 past 12, so I'm basically just going to say this and stop. If you were at my public lecture last night, I there talked about the galactic center GeV excess. So this is a pretty well-established excess of gamma ray photons in the inner part of our galaxy. It's centered roughly on the galactic center. It falls off away from the galactic center, and at least in its inner region, it has a very spherical shape. So these plots are showing what we found when we looked at the Fermi galactic center. The reason for the black band across the middle of the plot is that we masked the galactic plane. The reason for the black splotches is that those are places where big point sources have been masked. And these are 4 different energy bands. But this sort of green blob of emission around the center is the excess. This excess got a lot of attention as a possible signal of dark matter annihilation, partly because if interpreted as dark matter annihilation, it comes from the dumbest possible dark matter model. It's order 50 to 100 GeV dark matter particles with a thermorelic cross-section. Now, you can change exactly what your best fit is depending on how you model the backgrounds. There are also, so you may notice, a thermorelic cross-section with a mass scale of 50 to 100 GeV is the same mass and cross-section range as that 0 to 5 sigma antiproton excess that I told you about earlier. Now, the antiproton excess may be 0 sigma, depending on what you assume about the background, so you probably shouldn't consider it as a confirmation. But if you are very optimistic, there is a picture where this is a dark matter signal, and also the antiproton excess is real and is pointing at the same thing. And there are also faint hints of possible corresponding gamma ray excesses in a couple of dwarf galaxies. Although again, the significance is 0 to 3 sigma depending on how you count. So should not be taken too seriously. I mean, the pessimistic interpretation is that this is all pulsars and the others are statistical fluctuations. And I think that's also quite consistent with the data. But there is an optimistic story where this could actually be a dark matter signal. There have been several studies that found evidence for a non-dark matter origin, and the most frequent hypothesis, as I said, is that this is actually coming from some new and previously unknown population of millisecond pulsars in the galaxy. Probably the best way to test this hypothesis is that radio telescopes are coming online over the next few years, that if this is really coming from pulsars, they should be able to find the pulsations. So that would be how we establish that. There have been a number of studies that claim indirect evidence that this is coming from not dark matter, from looking at the shape of the excess as you move out from the galactic center, and from looking at the level of fluctuations from pixel to pixel within the excess. I think those are good analyses, but they are subject to significant systematic uncertainties on the background modeling, and we just showed, my postdoc Rebecca Lean and I just showed for one specific one of these strategies that it really is vulnerable to uncertainties in the background modeling, and that it can't find a dark matter signal on top of this data if you give it a dark matter signal that's much larger than the excess. So this is, again, a place to maybe stay tuned. And I'm happy to talk more about this, but maybe at lunch. So I'll thank you all for attending these lectures. I hope you got something out of them. Thank you very much for inviting me to the school and for asking excellent questions.
Thank you very much for coming and giving so energetic and very exciting lectures.
Thank you very much.